Here's a new video on potential vorticity, and it's just simply the next topic in SO 441 synoptic. Alright, let's get straight into it. I'll show you quickly what the objectives are. Same stuff you're going to get in class as always. We want to be able to interpret the physical meaning of potential vorticity, and we want to understand and be able to describe conservation of potential vorticity. And that needs to include the assumptions that must be made to say that it is conserved. And then we want to be able to explain where and why ridges and troughs are likely to form when we get zonal flow. And if you recall that zonal flow is west to east flow, or just east-west in general, but we almost always see it from west to east in both the southern and northern hemisphere in general, in the westerlies. So we want to understand what's going on there and why we see ridges where we see them, and why we see troughs where we see them with respect to zonal flow over terrain. So without further ado, let's get going to the actual topic. If I seem a little out of sorts, it's because the slide deck that I'm teaching from is slightly different than the one I have printed out in front of me. So I'm going to be going back and forth and trying to figure out, how the best way to portray this is actually going to come across in the video. So let's just get to the concept of potential vorticity. We've learned about the different types of vorticity. We have relative vorticity, which is, and I'll simply write it down over here, zeta equals dv dx minus du dy. And to make that geostrophic relative vorticity, we just add Vg and Ug, which means the U and V components of the geostrophic wind. And we have zeta A, which is equal to zeta plus F, where F equals 2 omega sine theta, or in some cases you see phi. But either way, they both equal latitude. So now we're going to talk about potential vorticity, which is actually taking the vorticity in the entire column of air and averaging it by height. And what we end up with is this equation down here at the bottom. And I'm going to circle that real quick. Potential vorticity equals relative vorticity plus Coriolis divided by height. So the concept of potential vorticity, back up to the top here, and I'll do a highlighter, is that you take a column of air defined by two potential temperature surfaces, theta and theta plus del theta, and I'll draw that down here at the bottom. So all that's saying is we have the surface of the Earth, down here with trees and whatnot, and then we have the top of the troposphere. Now it's defined in the concept up there as in terms of theta, but recall that theta is potential temperature, and it's just simply you take a parcel and bring it down dry adiabatically to 1,000 millibars. At the surface we can assume we're about 1,000 millibars, so here's your theta, and here's your theta plus del theta. So some different value of theta. And if you recall from SO 345, atmospheric thermal, that if you brought something down adiabatically from the top of the troposphere, it would be pretty warm due to adiabatic compression. So this is a higher value of theta than this. So we're going to call this top of the troposphere. And again, trying to write as clearly as possible on a computer screen. And this is surface. And this next step here is move the air column eastward or east-west over a mountain range. And I'll draw that in real quick. Tell you what we mean there. Now I throw a mountain range in here. So I've got this column of air here, which is moving from west to east. So we're going to take it over here. What's going to happen to that column? Well, when we set it up over terrain, it's going to get shortened and squished. And then when it comes over here on the other side, it's going to elongate again. So it's compressed, then stretched. And we're going to figure out what the relationship is between all the variables here in the PV equation as we try to conserve, not as we try to. Potential vorticity is conserved if we assume certain things. So this whole chapter is about what happens to the column of air? Well, it compresses and fattens. We see that here as it approaches the mountain and stretches again on the other side. So here's compression, here's stretching. And mathematically, what happens within the equation? So here's your equation. This is something you'll need to know, what that actually is, and how the variables change with time. So we've got this drawing. Now let's move on as we step through the process of thinking about what's actually going on. So physically, potential vorticity is the quantity that we use to measure the spin up or spin down of that column as it goes over terrain. And we're assuming large scale, like as in the entire west coast of the United States has a mountain range, the entire west coast of South America has a mountain range. And we also have to assume that it's adiabatic. So, conservation of potential vorticity. This concept is defined by this equation down here, which is the change, the material derivative of potential vorticity with time is 0. What does that mean? It means this equation must always have the same value. The initial value, if we go back up here, the initial value here, there's a certain value. You can do that calculation. How much relative vorticity does it have? How much Earth's vorticity does it have? And we define the height as from the surface of the troposphere, what's, in general, 10 to 11 kilometers. And we then take it up and over that mountain. What changes to the variables inside? So we must assume this is one of your objectives. You need to know what the assumptions are and what it means to conserve potential vorticity. So in order to conserve potential vorticity, we need to assume that we have frictionless flow. And not only do we need frictionless flow, but we need adiabatic flow. So the air masses warm and cool adiabatically as they go up and over the mountain. So potential vorticity is conserved following the parcel if we assume these two things. As in, there's no friction to dissipate the spin. And your Coriolis, the F parameter, 2 omega sine phi, or theta, 2 omega sine theta, is simply a function of theta, because rotational rate of the Earth is constant. So the only thing that would cause Coriolis to vary is your latitude. So what does it mean that we need to assume adiabatic, by the way, is we need to say that we have no diabatic heating, i.e. no energy added to the parcel. No absorption of radiation from the sun, no absorption of heat from conduction between the parcel and the environment around it, etc. So we need to assume adiabatic, we need to assume frictionless. So this, you might recall, the big D, little t, is material derivative. And the material derivative means that we are following the parcel. We stick with that parcel from one side of the mountain to the other. And that parcel, similar to conservation of momentum, it has to maintain a certain amount of energy. That's why we call it potential vorticity. It's because it has the potential to do things, and we just need to change its environment to either spin it up or spin it down. And now we're going to move on and take a look at what that actually means. How do we spin it up and how do we spin it down? So return to the scenario of the easterly flow. We've got a fluid column that moves from west to east. So easterly, or this should be like, that's a bad term. So we'll cross that out and say westerly flow. That's not the appropriate way. We're saying from west to east, so westerly flow. And in just a second, I'm going to scroll this up after I go through what we're talking about here and redraw the picture down to get this example that I would put on the whiteboard in class. So we have the westerly flow, same picture as before. Along its path, potential vorticity must be constant because we've defined that if we assume frictionless flow and we assume adiabatic, that potential vorticity is conserved. That column of air has a certain amount of spin to it that it needs to maintain, similar to an ice skater again, I keep on going back to this analogy. The ice skater with the hands out wide will spin slower if the hands come in and we have stretching, like if you recall in the extratropical cyclone development discussion, we stretched that column, we made it tall and thin, and it starts spinning faster. Similar concept to what's going to happen here. We got Earth's vorticity. It's constant because we are moving east-west. Latitude is not changing. H is simply the height from the surface to the top of the troposphere, and that's going to change as you go over the mountain. Notice it decreases as you go over the mountain. And we'll talk through the relative vorticity. The zeta must decrease. Then after passing over the mountain, the depth will increase again, and we're going to talk through the mathematics of vorticity, relative vorticity. Will have to go up also as h increases. So I'm going to scroll down here, redraw the picture, and then start this video again. So it doesn't skip around. I'm going to scroll right now. So I'm going to redraw the picture down here below the example on the whiteboard, and we'll talk about the math that's going on. Okay, let's take a look at this example. We've got the column of air prior to going over the mountain. So right here in yellow, we got the column. So the yellow is prior, green is while it's going over the mountain, and purple is after it has gone over the mountain and stretched again. So let's take a look at what's going on, and I've got a few example, let's assume that we calculated zeta 1, relative vorticity of 0.1, 1, 2, 3, they're numbered, and we said it's 1 times 10 to the minus 5th per second. And F1, we calculated that based on the Earth's rotation rate and the latitude that we're at for this particular question. And we calculated that at 1 times 10 to the minus 5th per second. That's second to the minus 1, by the way. So you can do a calculation of PV equals 1 times 10 to the minus 5th plus 1 times 10 to the minus 5th over 10 kilometers. And that equals 2 times 10 to the minus 5th over 10 kilometers. Okay, since we are saying that we're conserving potential vorticity because we are assuming frictionless flow, we are assuming adiabatic, we move over to position 2. So this is PV1. PV2. What's actually happening within the equation? Well, we've got zeta 2. And what do we know about F2? Since we have east-west flow, this is zonal flow. Does latitude change? No, it does not. So F1 is the same as F2, which is the same as F3. So we can do plus 1 times 10 to the minus 5th. This time we're saying the height at position 2 is 1/2 the original height, so we're going to say 5 kilometers. So if I went to a common denominator and went to 10 kilometers down at the bottom, what you would see is that if I put this over 10, I've got zeta 2 plus 2 times 10 to the minus 5th. So what does that mean if I'm conserving, if the change of potential vorticity with time is equal to 0, the ddt is 0, and I've got 2, if I went to a common denominator of 5, so that's 2 times 10 to the minus 5th. What does zeta 2 have to be? Well, zeta 2 equals 0. Zeta 1 was equal to 1. Now let's move back to the picture and show position number 3. Again, PV3 equals zeta 3 plus 1 times 10 to the minus 5th for F, because it's the same as position 1, over 10. So what does that mean zeta 3 has to equal? Well, it's the same thing as zeta 1. So zeta 3 equals 1 times 10 to the minus 5th, second minus 1. So what does that mean? When I went up over the mountain, it's flattened, the height decreased, and therefore relative vorticity decreased. It went down to 0. It doesn't always go down to 0. It just worked out that way with our numbers. It could go negative. It could go less positive. But the reality is vorticity is decreasing. So you can almost equate that to negative vorticity advection. Vorticity will decrease with time with negative vorticity advection. So what type of motion would you expect? Like air motion, large-scale motion over terrain, you would expect downward motion. Where do you expect downward motion? You expect downward motion in a ridge, or at least downstream of the ridge axis. Where do you expect upward motion? Upstream of a trough axis. So as we went from zeta 2, position 2 to 3, what happened to vorticity? It went higher. So you went to positive vorticity. So you went from positive vorticity to no vorticity to positive vorticity. As we step from positive vorticity, 0 vorticity, and back to positive vorticity. So we would tend to spin up over here. You can almost equate that to positive vorticity advection. So positive vorticity is associated with troughs. So what you end up getting as we apply potential vorticity conservation, air moving over mountains promotes the development of ridges over and west of the mountains. Decreased heights result in decreased vorticity, and it can and will go negative. Negative vorticity is associated with ridges in the northern hemisphere. Air moving over the mountains promotes development of troughs on the lee side of the mountains. Lee is not the windward side, but the leeward side, downstream of the wind. Increased height results in increased vorticity due to conservation of PV. Positive vorticity is associated with troughs in the northern hemisphere. So we will see that pictorially in just a moment, but we're also going to now take a quick look at potential vorticity in the real atmosphere. We don't have much in the southern hemisphere. This is the southern hemisphere in the way of mountain ranges. We do have mountain ranges here on the west coast of South America, but the land masses are very small in the southern hemisphere. Now look at the northern hemisphere. These are 30-year averages of 500 millibar heights. And southern hemisphere is nearly symmetric. You can kind of see, a flattening here and a trough here as winds go from west to east in the southern hemisphere up and over the Andes Mountains. But take a look at the northern hemisphere. We have larger mountain ranges, and we have more mountains and land in general. So you can see you got this ridge off the west coast of the United States, 30-year average, and you got trough in the east on the lee side of those mountains. And the same thing happens in the mountains in Europe to a lesser extent, and the mountains in northern Asia. So this is the ridge that you have seen on a daily basis show up in the 500 millibar heights in the water vapor imagery. That's why it pretty much never moves, and when it does move, it replaces itself pretty quickly due to conservation of potential vorticity. And another thing you can see with potential vorticity in the real atmosphere is here's two different locations. This is 200 millibars, so way up in the atmosphere, and this is 700 millibars. You can see more pronounced effects down low where the air is actually interacting with the mountain. Because when we're drawing the picture, note that when we compress over the mountain, it's kind of compressing from the bottom up, so you're going to feel that effect, that spin up in vorticity, probably a little bit more towards the bottom, but averaged over the height, it's got to be the same, right? So you're going up from the bottom. There are sometimes a little bump above, but it's not as big as the mountain itself in the upper level. But the reality is it's more pronounced down at lower levels. And moving on to a real scenario, just not one that we're used to looking at in the northern hemisphere, is we've got the Andes Mountains going right through here. And what you end up with is a ridge of high pressure kind of over the mountains, followed by a trough in Argentina. So here's your ridge trough scenario. Granted, these are surface pressures, but you get the picture. You end up with highs typically over the mountains, and you end up with lows on the lee side. It's the reason we get Alberta clippers. It's the reason we get Colorado lows during the winter. You see lows popping up in Colorado from conservation of potential vorticity because of that stretching on the lee side of the Rocky Mountains. So Colorado, Kansas, western Kansas area is normally a generation area for surface lows because you have lee side troughing from flow over the Rockies. That is pretty much it. That only took 20 minutes. That's everything. It's probably going to take 2 classes to get through all of it though. But I'm posting the video and we'll move on to the next topic when required.